So in this video, we're looking at factors and multiples, which are kind of two sides of the same coin. So I have some definitions here, but another way of thinking about them is that factors, if we start with this one here, factors are the numbers that you can take and multiply to get a bigger number. So what I mean by that is we'll say, well, what are the factors of 30? Well, what that means is what whole numbers multiply to get you 30? Well, we have 2 and 15, we have 3 and 10, and so on and so forth. So that's what we mean by factors, are the smaller numbers that can multiply together to get this bigger number that you're looking at. So the factors will always be equal to or smaller than the number that you're looking at, because you cannot have a number that's bigger than 30, yet multiply it to get 30, because you're only dealing with whole numbers here. You're not dealing with decimals or fractions. Multiples are a little different. Multiples are basically what you would see on a multiplication chart. So for example, what if I want the multiples of 3? Well, that means 3, and then the next multiple of 3 is 6 because it's 3 times 2. And the next multiple is 9 because it's 3 times 3. And then 12 because it's 3 times 4. And then dot, 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 all the way down as far as you want to go. So the multiples are taking a number and then timesing it by 1, and then 2, and then 3, and then 4. And all those answers you get are the multiples of 3. So for example, 10 would not be a multiple of 3 because nothing times 3 gets you 10 because we're dealing with whole numbers again. But 6 is, 9 is, 12 is, 15 is, all the way down as far as you want to go. So the multiples will always be equal to or bigger than the number. For example, the multiples of 3, the smallest one is 3, and then there is no biggest one because it goes on forever. But the multiples can never be smaller than the number. The factors can never be bigger than the number. That's a trick you can keep in mind here. Multiples deal with multiplication. Factors deal a little bit more with division because you're taking a number and you're dividing it into its smaller pieces. Let's take a look at multiples here just a quick second. So how do you find the multiples of 6? Well, you just make a table. So you start with 6. That's 6 times 1. Then 6 times 2. That's going to be 12. And 6 times 3. That's going to be 18. And 6 times 4, that's going to be 24, and on and on and on and on. So the way you get your multiples is just take a number and just multiply it through times 1, times 2, times 3, times 4, as many as you want until you're done. So again, this goes on forever, so just pick a point where you want to stop and then stop there. Same for 4. What's the first multiple of 4? Well, it's 4, because it's 4 times 1. Then the next one would be 8. Then the next one would be 12, and then 16, and then on and on and on and on and on. So you just make a list and you just times it by 1, then 2, then 3, then 4, then 5 until you get to where you need to get to. Again, these numbers will always be bigger than or equal to the number that you're looking at. So the multiples of 4 will always be bigger than or equal to 4, never smaller than 4. Now the LCM, which is the least common multiple, is basically when you make a multiple of two numbers and you pick the first or the smallest number that they have in common. So for example, let's do 3 and 5. So here's 3, here's 5. I'm just going to list out their multiples back to back or top and bottom, and then just pick the first one they have in common, the smallest one they have in common. So this is times 1. Obviously, they're not common yet. Let's do times 2. Well, 3 times 2 is 6. 5 times 2 is 10. No common number yet, so we'll do times 3. 3 times 3 is 9. 5 times 3 is 15. No common number yet, so we'll do times 4. 3 times 4 is 12. 5 times 4 is 20. No common number yet, so we'll do 5. So 3 times 5 is 15. 5 times 5 is 25. And here we have our common number 15. That's our first common number, our smallest common number that we'll have. So 15 is my LCM. Because if we go on any further, obviously the next number is going to be bigger than 15 here. And the next number is going to be bigger than 15 here. So we don't need to go any further. Once we hit the first number, that's their smallest number. So my LCM between 3 and 5 would be 15 because it's the smallest, the first common multiple they have in their lists. If we try 8 and 6, we could do it the same way. 8, 6, it doesn't matter which one you put on top and bottom. So this is obviously times 1, again, not common yet. So times 2, we get 16 and 12, nothing common yet. So times 3, we get 24 and 18, nothing common yet. So we times 4. We get 32 and 24, and here is where we have our common number. So our LCM in this case would be 24. That's the smallest common multiple they have. Now, if you knew that right away, because you know, well, 6 times 4 is 24, and 8 times 3 is 24, and it's the first number they're going to have in common, if you just know that because you know your multiplication tables well, then you can just say 24. You don't have to make out a list. But if you're new to this or you're not so good at multiplication yet, making a list like this can help you organize your numbers and therefore make your LCM a little bit easier to find. Again, you're looking for just the first common number that they have. Now, factors are a little different, or they're done in a kind of a common way. So factors are these small numbers that make up the larger number that you're looking at. So in this case, we have 20 here. Basically, you want to ask yourself what two numbers multiply to give you 20, and you want to do that until you run out of whole numbers, because you only deal with whole numbers here, not decimals or fractions. So what numbers multiply to give you 20? So we have 1 and 20, we have 2 and 10, and we have 5 and 4. So no other number, whole number at least, will multiply together to give us 20 other than these numbers listed here. Again, 3 won't work, 10 won't, well, 10 already works, we already have it listed down there, 6 won't work, and so on. And again, the numbers here have to be smaller than 20, because obviously nothing bigger than 20 will multiply to get you 20. So these would be the factors of 20. 1 and 20, 2 and 10, and 5 and 4. Same thing for 12. So we look at what numbers will multiply to give me 12. Well, we have 1 and 12, we have 2 and 6, and we have 3 and 4. And then if you go down the list here, 5 doesn't work, 6 we already have, 7 doesn't work, 8 doesn't work, 9 doesn't work, 10 doesn't work, 11 doesn't work, and then 12 obviously we already have, and then again, we can't go past 12, so that'd be the end of it. So those numbers would be the factors of 12, 1 and 12, 2 and 6, 3 and 4. Nothing else would multiply to give me 12, at least not whole numbers. Now if we try to list out for 7, so if we list out the factors for 7, we have 1 and 7, and then nothing else really. There's no other numbers. 2 doesn't work, 3 doesn't work, check all the way down to 7, nothing else works. And so because our factors are only 1 and 7, that's what we call a prime number. So a prime number is basically a number that you can only get by multiplying 1 and the number itself. So there's no other way to get 7 by multiplying except for just 1 and 7. You can get it by adding and subtracting and stuff, but as far as multiplication goes, the only way of getting 7 is by taking 1 times 7, at least for whole numbers. Again, decimals and fractions will give you different avenues, but as far as whole numbers go, the only way of getting 7 is taking 1 times 7. 2 is another example. The only way of getting 2 is 1 and 2. There's no other combination of numbers that will multiply to give you 2. So the next thing we have for factors is GCF. So LCM is kind of like, for multiples, GCF is the counterpart for factors. It's the biggest common factor that people have, that two numbers have in common. And the way you figure it out is you just simply list the factors of each number and then find the biggest one that they have. So we have 8 and 12 here. So I'm going to list out the factors for 8. So 1 and 8, 2 and 4. I'm going to list out the factors for 12 because 8, that's the end of 8's factors. So 12 is 1 and 12, 2 and 6, 3 and 4, and then nothing else. So basically I want to say, okay, what's the biggest number they have in common? Well, here it's 4. So my GCF then is 4. So again, the GCF is just the biggest factor that they have between them that's the same in each list. So obviously 2 is a common factor and 1 is a common factor, but the biggest common factor in this case would be 4. Let's do 10 and 20. So 10 over here, 20 over here. How do we get 10? Well, 1 and 10, and 2 and 5. And that's about it. What about for 20? Well, we have 1 and 20, we have 2 and 10, and we have 5 and 4. So if we look at this list here, the biggest common factor in this case is 10. So my GCF would be 10. So your GCF can be one of the numbers themselves as well. That's fine. In fact, if one of your numbers is a factor of the other number, it's automatically going to be the GCF. So for example, 6 and 12. 6 is a factor of 12 already, so my GCF is automatically going to be 6 because 6 will have no bigger factor than 6, and it's already going to be in the 12 list, so 6 is my GCF. So if you know that trick right there, you can save yourself some work. Otherwise, you can just make up the list and do it that way. Again, all you're doing is listing out the factors and finding the biggest one they have, in common at least. Now, prime factorization is a little bit different. So prime factorization is when we want to break down the number into its kind of like its DNA. So it's all the small primes that you can multiply together to get the number that you're looking at. Excuse me. So it's kind of like like I said, the DNA of a number. So I want to figure out, okay, how far can I break down 60 using whole numbers? How far can I break down 60 until it's just prime numbers multiplied together? So if we take a look here, the way you do this is you make what's called a factor tree, which is basically just factoring it again and again and again and again and again. So you want to ask yourself, what two numbers multiply to give you 60? Well, 6 and 10. 6, 10. Then you can go to 6 and say, is 6 prime? Well, no, because I can split 6 again. I can split 6 into 2 and 3, so it's not prime, so I'm going to do that. I'm going to split 6 into 2 and 3. Then you're going to look at 2. Can I split 2 anymore? Well, no, because the only way to split 2 is by doing 1 and 2, which, again, you don't want to use 1 because 1 can go on forever, because just 1 times 1, and then 1 times 1, and then 1 times 1. So 2 is prime, so that branch is done. Same for 3. 3 can't be split into anything other than 1 and 3, so 3 is done. 10 can be split into 5 and 2, and we already know that 2 is prime, so we'll stop that there. 5, again, it's only 1 and 5, so 5 is also prime, so we'll stop that branch there. So the prime factorization of 60 would be this: 2, which is this one, times 2, which is the next 2, times 3, times 5. Or if you want to write it a different way, you can say 2 to the second, because there's two 2's. So 2 to the second times 3 times 5. Both these would be okay answers. And again, your prime factorization, like I said, is kind of like the DNA of a number. So you're not going to actually multiply them together. You're just going to kind of show that 60 is broken down into 2 times 2 times 3 times 5. That's how you break down 60. That's the farthest you can go and factor down 60 using whole numbers. So your answer to a prime factorization problem is a list of numbers multiplied together. So again, they can kind of see what 60 broken down would look like. So if we try a bigger number here like 120, what numbers multiply to give you 120? Well, we have 12 and 10. 10 we know breaks down to 5 and 2, and those two branches end there. 5 is done and 2 is done. 12 breaks down into 3 and 4, and 3 is prime, so that branch is done. And then 4 breaks down into 2 and 2, so that's done there. So my final prime factorization is 2 times 2 times 2, because I have 3 2's, and times 3 times 5. Or put another way, 2 cubed times 3 times 5. Either way would be okay. But again, this is kind of like the DNA of 120. 120 breaks down to these numbers here, and that's it. So both these answers would be just fine. Same with 24. Again, your factor tree might look different because there's many ways of doing the factor tree, but your end answer will always be the same. So no matter how you start your factor tree, your final answer will always be the same. So 24 we can break down to 6 and 4. And then 6 we can break down into 3 and 2. And those are done. And then 4 breaks down to 2 and 2. So those are done. So my final answer then is 2 times 2 times 2 times 3. And that's my prime factorization. That's the DNA of 24. All the numbers that you can multiply to get to 24 as primes are there. Now, if you did this a different way, let's say you started a different way. Let's say you did 12 and 2. You still get the same answer. So we have 2 and 12. That's done. 12, we can do 6 and 2. Well, that's done. And then 6, we can do 3 and 2. And both those are done. So my answer is still 3 2's and a 3. So no matter how you start your factor tree, your final answer will always be the same, assuming you split your numbers correctly. So you don't have to worry about how to start it. Just pick the two first numbers you know, multiply to get you that bigger number, and then go from there. Okay? Usually using 2's and 3's are helpful because those go into a lot of numbers. That's it for this video. Hope you enjoyed the video. Have a good day.